Hello and welcome to this video, and today we're looking at nucleophilic addition reactions. Okay, so nucleophilic addition. So the first thing I want to talk about is this. Previously we've seen attack on a double bond. Now, as you know, I'm sure, this region is high in electron density. Okay, and therefore what's going to attack this? A nucleophile is going to attack this, something like bromine molecule, and an induced dipole is formed on the bromine, and one of these carbons, or the electrons here, capture the bromine, and that goes on there, and we end up with a something like this. We end up with bromine across the double bonds. Okay, there you go. Now, the amazing thing, the thing to notice about this is the attacking species, in this case the bromine, the attacking species is attacking electron density, negative charge, the negative charge cloud. Okay, so it's attacking a negative charge cloud, and therefore the thing that's attacking it is called an electrophile. Okay, and it's an addition reaction, so overall this is known as electrophilic addition. Okay, electrophilic addition. That's the electrophilic addition. Now, I'm bringing that up because it's different to what we're doing today. And today we're doing nucleophilic addition. So this one is going to be nucleophilic addition. Okay, and what happens now is a nucleophile attacks this carbon here, which has a positive charge, because oxygen is more electronegative than carbon. And what's going to happen is something's going to attack this carbon. And the thing that's going to attack the carbon is a nucleophile. Okay, and these electrons are going to go there, and then we're going to get something else. So let's have a look at the nucleophile attacks it, and we're going to get something like this. The nucleophile is going to bond onto that carbon. Let me get rid of that little weird thing. Okay, there. And this O minus here is then going to capture a proton from somewhere, and we're going to get this. We're going to get the nucleophile, carbon, and OH. And this is going to be nucleophilic addition. Okay, there you go. So, this is nucleophilic addition. So it's two things coming together to make one thing. All right. As you can see, or you may be able to see, that this thing here, this carbon here, because it gets two more groups around it, is often chiral. So this mechanism gives rise to chiral carbon atoms. All right, so let's have a look. What have we got then? Now we're going to add two carbonyl groups, and I'm going to add, let's have a look. Let's have ethanal to start with. Ethanal, which is an aldehyde. Okay, let me draw the structure of ethanal. It looks like this, CH3 and CHO. Okay, there's ethanal, and it's going to attack the carbonyl groups. So what we're looking at now is ethanal, and we're going to look at the nucleophilic attack on carbonyl groups. Carbonyl compounds, I should say. Now, carbonyl compounds are either, try and get a different colour, make this look a bit more interesting. Carbonyl compounds are either aldehydes or ketones. So we'll have a look at attack on those two. Now, what's the nucleophile in this case? Well, the nucleophile we're going to use is hydrogen cyanide. There's the cyanide group, and there's a hydrogen. Okay, so this is going to attack. This is going to add across our CO double bond. So this is going to add across our CO double bond. All right. There you go. It's going to add across the carbonyl group there. All right. So a few things we've got to know then. First of all, HCN is a weak acid. So this will dissociate like this, okay, into the hydrogen ion and the cyanide ion. Okay, now unfortunately the cyanide ion, there's not many of them. Why aren't there many of them? Because HCN is a weak acid. And we want this to be our nucleophile. And there's not many of them. All right. So before we go on, let's have a look at a nucleophile. Let's have a look at this particular nucleophile. This is the carbonyl compound. Sorry, this is the cyanide ion. All right. And the cyanide ion looks like this. It's got a lone pair on the carbon and a lone pair on the nitrogen. The whole thing is negatively charged. So this is the cyanide ion, and this is our nucleophile. And because HCN is a weak acid, we're not going to get too many of those. So we have to do something a bit sneaky. And the thing we do is we introduce sodium cyanide to the whole thing. So sodium cyanide is added to initiate the reaction, to start the reaction off. Okay, and basically this looks weird, I think, but a cyanide ion, for every sodium cyanide we put in, a cyanide ion is regenerated. So this guy here, this is acting as a catalyst, and you'll see how that happens in a minute. So this eventually turns into a catalyst, but it initiates the reaction, but you get one of these regenerated at the end, and you'll see how. Okay, so let's do the mechanism. Right, so we're assuming we've got cyanide ions floating around from the sodium cyanide. Okay, so here is my CH3, and don't forget we're using ethanal, aren't we? There's my CO, and there's my hydrogen. Now, this is partially positive, this is partially negative, and this thing here, this part of the molecule, okay, is planar. Okay, this is trigonal planar. So I'm going to draw my CN coming in from here. Here is the CN. There's the lone pair on the carbon. There's also a lone pair on the nitrogen. Okay, and the CN is going to come in and attack this, and at the same time these electrons are going to go there. Now it doesn't, the way it looks like I'm doing this, it's coming from the side, but because the CHO bit, this bit here, okay, if you can imagine this whole thing is flat, and the attack is either going to come, let me use the right color, the attack could come from the bottom, there's the CN attacking from the bottom, or it could come from the top, okay, of this planar part of the molecule. Okay, so there it comes from the top. All right, so it looks like it's coming from the side, but it's either coming from the top or the bottom because the thing's planar. All right, so what do we get? Well, we don't get that. What do we get? We get this, nice arrow there, and this cyanide sticks onto that carbon. So there's my cyanide. It's going to stick onto the carbon, and that new bond, that's the new bond, formed by the electrons on the cyanide ion. This is the CH3 at the top, this is the H at the bottom, and there's the O minus, formed by the electrons going onto the oxygen. So this has lone pairs on it, doesn't it? Okay, so there you go. That's the intermediate. All right. Okay, now, and this is the nice bit, I think, anyway. What color shall I use? Let me use green. Now there's a passing, that sounds weird, a passing cyanide ion here. Now the cyanide ion, this part of the molecule is delta negative, and this part is delta positive. So what happens now is these electrons from the oxygen go out to capture this hydrogen, and at the same time, the electrons go onto the cyanide ion. So this now becomes this. Okay, so you have this is my cyanide that was added. There's the original molecule, I guess you call it. There's the O, and there's the H. Okay, so can you see HCN has been added across the double bond there. The CN's gone on one side, and the H has gone on the other. That's why it's called a nucleophilic addition. Okay, and what's the other thing we get? As you can see here, we also get cyanide ion. So interestingly, we started off with the cyanide ion. HCN adds across the double bond, but we regenerate a cyanide ion. So the NaCl is kind of regenerated, and therefore it's known as a catalyst. Okay, HCN is used up during the reaction, but every time the reaction happens, one CN goes to bond onto the ethanol, and another one is regenerated. Okay, so there you go. That's a nucleophilic addition reaction. So let's have a look at this. This is nucleo because the original thing attacked a positive center. So this is nucleophilic and it's addition reaction. Okay, and this is on the carbonyl bit of an aldehyde. Okay, so very quickly, I don't know how long I've been going, but it's probably too long already. All right, I'm going to do exactly the same with a ketone now. So it's exactly the same reaction. Okay, there you go. This is now a ketone. All right. Same thing happens. This is delta plus. This is delta minus. The CN comes on from here. There's the lone pair. That goes on there. That goes over there. And we get a CN again. Goes on to the original molecule. So there's a CH3 there. There's a CH3 here. Oops. There's a CO. It's got its, that's purple ones now. It's got its lone pairs, and this is going to attack a passing HCN. All right, and these electrons capture that, and these electrons go onto there. Why do they do that? Because this is partially positive, this is partially negative, and what do we get? We end up with this thing. I'm trying to keep the colors consistent. C, oopsie daisy. So that's C, CH3, CH3, O, and this new one, H, plus the cyanide ion there. So there you go. You get that thing and the other thing. Let me get a nice shading thing. So that's the second one. That's with our ketone. And our aldehyde was this thing. Okay, there you go. So what's the difference? Well, obviously in this one, the top one here, we've got hydrogen down here. But if we use a ketone, we'll have an alkyl group down here. So that's the major difference. So if I do this one, what's this thing called? Right, now this is called, if you look at the longest chain here, it's 3 carbons in a row. So this is called propane nitrile. Okay, because of that bit, that's the propane nitrile. And there's something on my propane nitrile. There's a hydroxy group. And we say hydroxy, propane nitrile, and it's on number 2. So this is called 2-hydroxy propane nitrile. Oops, there's it. And this class of compounds, they're given a funny name. They're called cyanohydrins. Okay, cyanohydrin. Okay, so let's have a look at the bottom one here. Let's name this again. Well, it's the same length of carbon chain. So this is going to be propane, again, propane nitrile. There's 2 groups on my propane nitrile now. There's a methyl group there, and there's a hydroxy group there. Hydroxy. Now, hydroxy starts with H, methyl starts with M, so hydroxy gets its mention first. So this is called 2-hydroxy, 2-methyl propane nitrile. And again, it is a cyanohydrin. Okay, that's the name of it. The cyano bit is that, and the hydrogen, it's not that bit, it refers to that bit. Not that bit at all. Let me rub that out. Okay, so there you go. cyanohydrin. So that's nucleophilic addition to carbonyl compounds. Now, let's do very quickly the formation of a chiral center. Okay, and I will use the ethanal as an example. Okay, so here we start off with ethanal. Okay, and let's CO. Okay, oops, that's not an O, is it? It's an H. So I'll stick an H there. Now, if you remember, this kind of whole thing is trigonoplanar. So if the CN attacks from the top, okay, or the CN could attack from the bottom. So if it attacks from the top, we get kind of this thing, the CN, you get the C there, and everything bends down, as it were. All right, there, you get the OH, and you get the H, okay? So this is for this one. If it attacks from the top, everything will bend down from the CN. If it attacks from the bottom, you'll get the CN. If I've got some room for this, you get the C, you get the CH3, you get the OH, and you get this, what else have I got? The H. And if it attacks from the bottom, you kind of get this orientation. Now, if you see this, good for you, but these are mirror images of each other. Of each. That's not how you spell each, even vaguely. Each other. Okay, so these two, there's a chiral carbon and there's a chiral carbon. These are two enantiomers. Enantiomers. All right, in other words, two chiral compounds. Two optically active isomers. Two optically active isomers. Okay, and one will rotate plane polarized light anticlockwise, and the other will rotate plane polarized light clockwise. But as you can see, there's a 50% chance of it attacking from the bottom and a 50% chance of it attacking from the top. So you'll get 50% of this and 50% of this. So when we get optical isomers in a 1-to-1 ratio like this, it's known as a racemic mixture. All right, or a racemic mixture. Okay, and racemic mixtures, as I say, they're 50-50. Racemic mixtures do not rotate light. And the reason for that is because one isomer cancels out the effect of the other isomer. So you get no